The 28-nanometer process nodes used in smartphone processors that year implemented features that required positioning accuracy beyond what the most advanced lithography systems could theoretically achieve. According to manufacturing specifications published by equipment makers, the lithography machines available in 2012 had resolution limits that made certain smartphone chip features technically impossible to produce. This discrepancy becomes more pronounced with each passing year. The 7-nanometer process nodes in smartphones manufactured after 2017 contain transistor structures with features measuring less than 10 atoms across. Creating these structures requires positioning precision within 2 atomic widths, accuracy that manufacturing experts had calculated would not be achievable until the late 2020s. Yet these components appeared in consumer devices years before the manufacturing equipment supposedly capable of producing them had been invented. When semiconductor manufacturing experts examined these components, they discovered structures that couldn't be explained by known production methods. A senior process engineer at a major semiconductor fabrication facility stated in an industry conference in 2018, "The gate structures in these processors contain features that our lithography systems shouldn't be capable of creating. We're still trying to understand how these patterns form during the manufacturing process with greater precision than our equipment specifications indicate should be possible." Smartphone camera sensors demonstrate similar manufacturing anomalies. Modern phone cameras contain pixel structures measuring less than 0.8 micrometers with substructures requiring nanometer-level precision. Creating these sensors demands optical alignment capabilities and material deposition techniques that, according to photonics manufacturing experts, exceeded what commercial production equipment could achieve when these sensors first appeared in smartphones. Yet these impossibly precise components have been manufactured by the billions. The radio frequency filters in smartphones present even more extreme examples. These components contain acoustic resonator structures with precisely sized cavities that filter specific radio frequencies. Manufacturing these filters requires depositing materials and layers just a few atoms thick with perfect uniformity across millions of individual filters. According to materials science experts, the precision required exceeds what commercial thin film deposition equipment was capable of at the time these components first appeared in consumer smartphones. A thin film deposition specialist who examined these components observed, "The layer uniformity in these filters exceeds what our best deposition equipment can achieve even under ideal laboratory conditions." Commercial production of these components at smartphone volumes would require manufacturing precision we haven't yet developed, let alone deployed at scale. The manufacturing timeline discrepancy extends to nearly every miniaturized component in modern smartphones. The accelerometers and gyroscopes contain mechanical structures measured in nanometers that sense minute movements through electrical changes. The non-volatile memory chips contain storage cells approaching the size of individual atoms. The battery electrodes contain nanostructures that shouldn't be possible to mass produce with known techniques. In each case, the components appeared in consumer devices before the manufacturing technology supposedly required to create them had been developed. This compressed miniaturization timeline defies all previous electronic component size reduction patterns. Historical data shows electronic components typically shrank by approximately 30% in linear dimension every 5 to 7 years, a pattern consistent across multiple technologies from the 1960s through the early 2000s. Smartphones accelerated this rate dramatically, achieving 80 to 90% size reductions across multiple component types within the same 5 to 7 year periods. This acceleration cannot be explained by incremental improvements to existing manufacturing processes. Manufacturing experts have struggled to explain this discrepancy. A semiconductor equipment specialist with 3 decades of experience examining production processes made this observation in a 2019 industry publication. "I've toured the facilities supposedly manufacturing these components, and the equipment I observed shouldn't be capable of achieving the precision evident in the final products. There's a missing link in our understanding of how these components are actually being produced at these scales." Similar testimonies come from experts in various manufacturing specialties. An optical engineer who designs photolithography systems stated in a technical forum, "The feature sizes in current smartphone processors exceed what our most advanced production systems should be capable of creating. Either the physical limitations we've calculated are wrong, or there's an aspect of the manufacturing process we don't understand." The precision extends beyond just small size to include perfect structural uniformity across billions of identical components. Manufacturing at nanometer scales typically produces significant variation between supposedly identical components, a fundamental aspect of production at scales where quantum effects begin to dominate. Yet smartphone components show uniformity rates that manufacturing experts had calculated were theoretically impossible at their production volumes. The manufacturing equipment supposedly creating these components raises additional questions. The extreme ultraviolet lithography systems required for advanced semiconductor production cost approximately $120 million each and occupy spaces larger than tennis courts. The precision required for smartphone component production would necessitate even more advanced systems. Yet no commercial manufacturer has publicly documented the existence of such equipment, despite the billions of advanced components being produced annually. This gap between theoretical manufacturing capabilities and actual smartphone components suggests advanced production techniques may have been reverse engineered from non-human sources. While conventional manufacturing follows step-by-step advancement with each generation building incrementally on previous capabilities, smartphone component manufacturing appears to have skipped multiple generations of expected development, implementing production precision that engineers hadn't yet figured out how to achieve. The evidence points to a disturbing conclusion. Internal smartphone components demonstrate engineering beyond conventional human manufacturing methods. These components incorporate structural precision that existing production equipment shouldn't be capable of achieving. They implement miniaturization that broke from historical development patterns. And they appeared in consumer devices years before the manufacturing capabilities supposedly required to create them had been developed. Even more remarkable than these individual miniaturized components is how they've been combined into functional systems. Modern smartphones integrate dozens of advanced technologies, processors, memory, sensors, radio systems, display components, and power management into devices thinner than a pencil. This integration represents an engineering feat that, according to system design principles, shouldn't be possible with current human knowledge. The seamless operation of these densely packed technologies defies conventional understanding of electromagnetic interference, thermal management, and power distribution. The integration impossibility. Systems integration represents one of the most complex engineering challenges in any technology. Combining multiple sophisticated components into a unified functional system requires addressing fundamental conflicts between those components. Every engineer learns that certain technology combinations create inherent problems that must be managed through careful design compromises. Three primary challenges dominate system integration: thermal management, electromagnetic interference, and power distribution. Thermal management presents perhaps the most immutable constraint. Electronic components generate heat during operation, a physical reality that cannot be eliminated, only managed. When components operate in close proximity, this heat compounds, creating hotspots that can damage sensitive elements. Conventional engineering addresses this through heat sinks, thermal paste, specialized materials, and active cooling systems like fans. Each of these solutions requires physical space, the one resource smartphones simply don't have available. Electromagnetic interference creates the second major integration challenge. Electronic components emit electromagnetic radiation that can disrupt the operation of nearby components. Processors interfere with radio receivers. Wireless transmitters disrupt sensor readings. Display drivers create noise that impacts audio circuits. Traditional engineering solutions involve electromagnetic shielding, careful component placement with minimum separation distances, and signal filtering systems, all requiring physical space and adding weight. Power distribution forms the third fundamental challenge. Different components require different voltages, current profiles, and power stability characteristics. Some need perfectly consistent power, others function with variable supply. Some components draw brief but intense current, creating voltage drops that can affect other systems. Conventional solutions include separate power regulation systems, extensive filtering circuits, and physical isolation of sensitive components, again requiring space that smartphones don't provide. System integration textbooks published as recently as 2008 explicitly stated that certain technology combinations were fundamentally incompatible in small form factors. One widely used engineering reference specifically noted, high-performance computing processors cannot be integrated within 2 centimeters of sensitive radio receivers without prohibitive interference unless separated by substantial electromagnetic shielding. Yet smartphones routinely place 2 to 3 GHz processors immediately adjacent to radio receivers that detect signals billions of times weaker than the processor emissions, all without the shielding thickness that engineering principles dictate should be necessary. The thermal management in smartphones defies conventional engineering understanding. Modern phones contain processors operating at clock speeds exceeding 2.5 GHz, generating substantial heat, yet maintain external temperatures safe for skin contact while continuing to function reliably for years. Traditional thermal calculations indicate this should be impossible in such confined spaces without active cooling systems. Engineers who have dissected smartphones express confusion about how the devices manage heat without the expected thermal management structures. A senior thermal engineer from a major electronics manufacturer stated in an industry conference in 2017, "The thermal spreading techniques in current smartphones achieve heat dissipation rates that exceed what our thermal modeling indicates should be possible given the materials used and the surface area available. The specific heat pipe structures implement principles we're still working to fully understand." Signal integrity presents another integration mystery. Smartphones contain dozens of radio systems operating simultaneously: cellular, Wi-Fi, Bluetooth, NFC, GPS, and others, all functioning without the interference problems that should make this impossible. The devices receive incredibly faint GPS signals that are billions of times weaker than the emissions from the processor located just millimeters away. Traditional RF engineering principles would require substantial shielding and separation to prevent interference, yet smartphones function without these expected protective measures. When RF specialists examined smartphone signal isolation systems, they discovered interference suppression techniques that implement principles not found in any other human technology. A communications engineer with 20 years of experience in RF system design observed, "The crosstalk suppression between radio components in modern smartphones exceeds what should be achievable at these separation distances. The interference cancellation appears to employ principles beyond conventional electromagnetic theory as currently understood." Power management in smartphones presents similar anomalies. The devices seamlessly handle extreme variations in power requirements, from nearly zero during standby to intense processing demands during gaming or video recording, while maintaining precise power delivery to sensitive components. This power regulation happens without the expected voltage conversion inefficiencies that engineering principles indicate should be unavoidable in such compact systems. A power systems engineer who analyzed smartphone power architecture noted, "The power conversion efficiency in these devices exceeds our theoretical models for what should be possible at this miniaturization level. The specific voltage regulation techniques implement topologies we haven't seen in other systems, with efficiency rates that violate our conventional understanding of switching regulator limitations." When examining the integration architecture holistically, engineers discovered that smartphones implement solutions not found in any other human technology. The specific ways components interconnect create synergistic effects that conventional engineering principles hadn't predicted were possible. The three-dimensional integration techniques stack and interconnect components in arrangements that appear almost biological rather than mechanical in their organization. Most telling is how certain integration techniques appeared in smartphones without the expected prerequisite engineering knowledge. The specific methods used to isolate sensitive components from interference sources implement mathematical approaches to signal cancellation that weren't documented in engineering literature when these smartphones first appeared. The thermal management systems utilize heat-spreading principles that emerged in commercial devices before they were described in thermal engineering publications. Multiple system engineers have acknowledged they don't fully understand how certain integration aspects function. A senior integration engineer who led development teams for a major smartphone manufacturer made this striking admission in an industry panel discussion. "We implemented certain system-level integration techniques based on reference designs provided by our component suppliers. The complete functionality of these integration approaches wasn't fully understood by our engineering team at the time. We knew they worked, but some of the underlying principles weren't clear to us." Another integration specialist with experience across multiple manufacturers stated, "The thermal and electromagnetic isolation in modern smartphones implements principles that weren't part of my engineering education or prior industry experience. Some of these techniques appeared to emerge fully formed rather than through the typical iterative engineering process. When independent laboratories analyzed the integration architecture in smartphones, they discovered organizational principles that don't match established engineering approaches. The specific way components interconnect creates system-level behaviors that exceed the capabilities of the individual parts, a characteristic more commonly found in biological systems than human-engineered devices. These integration techniques implement architectural principles not found in any other commercial electronics, raising questions about their origin. The timing of these integration breakthroughs raises further suspicion. The specific thermal management, signal isolation, and power distribution techniques that enable modern smartphone integration appeared nearly simultaneously across multiple manufacturers between 2011 and 2014. Despite these companies having separate design teams, different component suppliers, and proprietary engineering approaches, this synchronized implementation suggests a common source of integration knowledge outside normal industry channels. The evidence points to an unsettling possibility. The integration techniques in smartphones may have been derived from engineering principles not developed through conventional human research. The specific ways these devices manage competing technical requirements implement solutions not found in any engineering literature before their commercial appearance. They achieve integration density that established engineering principles indicated was impossible. And they implement architectural approaches that even their designers haven't fully explained. This integration knowledge appears to have emerged without following the normal progression of engineering understanding. It represents solutions to problems engineers hadn't yet recognized they would face as systems became more integrated. The seamless operation of densely packed, high-performance components within smartphone form factors remains one of the most compelling pieces of evidence suggesting influence beyond conventional human engineering knowledge. These sophisticated integration techniques enable all the other advanced technologies we've examined to function together as unified systems, creating devices with capabilities that should be impossible according to engineering principles understood when smartphones first appeared. The question becomes unavoidable. Where did this integration knowledge originate if not from conventional human research and development? As we've seen, your smartphone contains technologies that appeared without following normal development patterns. The historical record shows no precedent for such rapid advancement across multiple domains simultaneously. The materials inside your phone exhibit properties scientists couldn't explain just years before they appeared in commercial devices. Quantum effects function at room temperature when theory said they shouldn't. Semiconductors implement architectures that emerged mysteriously. Manufacturing precision exceeds equipment capabilities. We're left with a profound question. Is this all human ingenuity? Or were we guided by something beyond our world?